In this section, we'll talk about the max flow min cut theorem. And before we do that, let's summarize all the results leading into that theorem. We have seen this before, theorem 7.1. For any flow in a network, the total flow out of the source is equal to the total flow into the sink. And because of that, we can define that value as the value of the flow of the network. This means that we can measure this value of the flow by looking at all the edges or the arcs that are going out of the source, and we add all the flows, all the numbers at each edge, and the total is the total flow out of the source. And this theorem says that that is the same as the total flow into the sink. So we can easily find this value by adding all the flows, all the numbers on the arcs going out of the source, or all the arcs going into the sink. Next, theorem 7.2, it says that if we have a cut and if we have a flow in a network, then the value of the flow, which is the same value of the flow that we saw here in theorem 7.1, the value of the flow is the total flow from S to T minus the total flow from T to S. Now, S is the set of vertices in one partition in a partition of the cut, and where the source is, and T is the set of vertices where the sink is. So if we can add all the flows in all the edges going from S to T and subtract the total flow of all the edges going from T to S, then we should have the same value of the flow as we find when we add the total flow into the sink or the total flow out of the source. This means that if we do have a cut somewhere in the middle of the network, so here I only show the source and the sink. I don't show any edges here, but let's suppose there is, a network here, and there is a cut somewhere in there. Now we look at all the edges or the arcs going, through this cut. Some of the edges could go this way. Some of the edges may go, the reverse way. And so let me add one more arc here. Let me just do this way, going this way. Okay, so this side of the cut is the side S. It's where the source is. All the vertices and including the source are here on this side, and this side is the T side where the sink is. Now we look at all the arcs along the cut. And what this theorem is saying is that we look at all the edges, all the arcs going from S side to the T side. That will be this one here. Let me put that in a different color. That one, that one. If we add the total flow there, that will be the total flow from S to T, because those are the arcs going from S to T. And we add all the flows going through the reverse arcs, going from the T side to the S side. We add the flow here, here, and there. That's the total flow from T to S. When we subtract the two totals, we should get the value of the flow, which is the same number, which is the same total of the flow out of the source or going to the sink. That's what the theorem is saying. And we have a corollary that says that the value of a flow, F, is less than or equal to the capacity of a cut, ST. So this comes from the theorem because we look at this result here, that the value of the flow is the total flow from S to T minus the total flow from T to S. Well, we simply ignore this term here of this subtraction, right? This expression minus that expression, when we subtract this, then um, this means that this right side becomes bigger, greater than the left side. So let's take a look at that. Here, the value of the flow, let's call this value A. And in fact, that's what in the proof of the theorem, they use the value A. And let's call this one here B, and then this one C. Okay. Now B is always positive. The total flow is always positive. The total flow is always positive, and the value of a flow is always positive. So these are three positive numbers. So when we remove the minus C here, then we're taking nothing away from B. So B has to be greater than A, greater than or equal to A at least. So this says that the value of the flow F is equal to the total flow, is less than or equal to the total flow from S to T. And this is what we get. Now the total flow from S to T, that is actually less than the capacity, from S to T, which is really the capacity of the cut. The flow at any arc cannot be greater than the capacity of the arc. So if we add all the flows, then the total flow cannot be greater than the total capacity, that's how we define the capacity of the cut, is the total capacity of all the edges going from S to T. And that's what the corollary is saying, that the value of a flow F is less than or equal to the capacity of a cut. Next, we have theorem 7.3. It says that the value of flow F is equal to the capacity of the cut. That implies that the flow is maximal and the cut is minimum. Now, in any cut, we know that the value of the flow is less than or equal to the capacity. And very often we'll find cuts where the value of the flow is strictly less than the capacity of the cut. And that may give us an impression that we should be able to increase the flow from the source to the sink because we have room to increase along a particular cut. However, that's not always true because there may be another cut where there is no room. In fact, theorem 7.3 says that if you do find a cut where there is no more room to increase the flow, which means the flow is equal to the capacity, then you just found a maximum flow and a minimal cut. So that minimal cut is what we call the bottleneck, right? Maybe there's more space in other cuts, but that particular cut is where the bottleneck is. So that's the area of minimum capacity. And if the flow is equal to the capacity there is no hope. There is no way you can increase the flow from the source to the sink. Then theorem 7.4, it relates to the algorithm that we studied in the previous video. If at the end of the algorithm the sink is not labeled, then the present flow is maximal. And moreover, the theorem also says that the set of labeled and unlabeled vertices form a minimal cut, where the capacity is equal to the value of the flow. And this is interesting because when we apply the algorithm, if there is no more improvement, that means that the sink was not labeled, right? And when we look at the set of labeled vertices, that will form the S side of the cut, and the unlabeled vertices will form the T side of the cut. And that cut is a minimal cut, where at that particular cut, the flow will be equal to the capacity. Theorem 7.5 says that the capacity, if the capacities are rational numbers, then and we start with a zero flow, then the maximum flow will be reached in a finite number of iterations. So it guarantees that the algorithm will eventually end with a maximum flow. If the capacitors are all integers, then it's not difficult to see that because every application of the algorithm will increase by at least 1 unit. So eventually it will reach the maximum flow. Now, if the capacitors are all rational numbers, then there may be a danger of adding just a little bit every time and it will never reach the maximum. You can think of, for example, a number like 1/3, which can be represented by an infinite decimal expansion, right? 0.3333, and it never ends. So we could think that the algorithm will keep adding those tiny values and it will never reach uh, the maximum flow. However, it's easy to also prove that the algorithm will eventually end by simply finding the least common denominator of all capacities. If they're all rational numbers, we can represent them as fractions. So we find all the common denominator of all fractions, and we multiply them by the common denominator, making the uh, all the capacities integers. Then you apply the algorithm, and at the end you find a maximum flow, and then you divide by the common denominator. So it's also a maximum flow is also reached in a finite number of iterations. And finally, this is the final result from this chapter. It's the max flow min cut theorem. It's stated is very simple. It says that the value of a maximum flow is equal to the capacity of a minimum cut. So let's say you know that the value of a maximal flow is a certain number. Then the theorem guarantees that there is a capacity, there is a cut there in the network where the capacity of the cut will be equal to the flow, and that cut will be a minimal cut. And same thing, if you find a minimal cut in the network, the capacity of that minimal cut is the value of a maximal flow.